Thanks for joining our Few-Photon seminar. We are very happy to have Noah. Noah is a postdoc here at Stanford. He's been here about a year and a half. He works jointly in the lab of Marty Bayer and Dale which is his lab over in this upper building. He'll tell us a lot about the photonics and nonlinear optics, things that he has done. Before this, he was a graduate student with Jeffrey Moses at Cornell, and before that, Berkeley. So I guess it's kind of, yeah. Anyways, yeah, enjoy.
All right, yeah, thanks for having me and thanks for the introduction. So if you were here last week, you heard about ultrafast pulses from Phlemens that contain many, many photons. Today we're going to talk about ultrafast pulses that contain very few photons. So primarily what this talk is going to be about, of course, is from the title, programmable nanophotonics. And in particular, I'm going to focus on these ultra-fast gates that leverage some kind of novel nonlinear optics to very efficiently switch ultra-fast pulses on the scale of 40 femtosecond. So, but before we get really into that, I want to do a review of nonlinear optics, then we can get to programmable ultrafast nanophotonics, and then we can talk about some of the challenges of scaling these systems to few photons. So, could I see a show of hands maybe of who has actually studied nonlinear optics formally? Okay, so we're sitting at maybe 15% or so. So this will be a good review for everyone. So I'm excited to tell you about the joy of nonlinear optics. In the laser world, we don't have a whole lot of linear gain media to produce lasers, all those sort of things that we want. So what we do is we use nonlinear optics to mix and blend and broaden the lasers that we have so that we can paint these happy little photons all over the electromagnets. So I'll talk about a couple of different nonlinear processes that are going to be important for this talk. The first one is optical parametric amplification. These nonlinear processes that I'm talking about involve the second order electric susceptibility of a material. So you're probably used to the first order electric susceptibility, which is responsible for the index diffraction and linear gain and loss. But here, kind of two is what we use to mix laser fields together to change their frequency. So in optical parametric amplification, we have a full oscillatory conversion between our pump field shown in green here and our signal field shown in red. And to get a semi-classical intuition for how this process works, we can think about this in terms of how photons are. So if I want to create a signal photon, I have to remove a pump photon. And that generates two signal photons at a time to conserve energy via this virtual level diagram. So this process continues on, remove one pump, create two signal photons, until eventually what's going to happen is we fully convert the pump to signal. At this point, we call this saturation. Now the process is going to reverse, and to create a pump photon, we remove two signal photons. And this process is called second harmonic generation because we take two photons at frequency omega and create a photon at frequency beta. Now, there's another nonlinear process that we're going to want to understand, which is slightly different. Now, this is a two-dimensional process called sum difference. And what we can see here is that instead of having a full exchange of power between all the fields, we're actually just changing the frequency of one of the fields. So the way that this actually proceeds is that we have what I'm going to call a gate field, or I might interchange that with pump field, but it means the same thing. And here we can see from our virtual energy diagram that to create our output field at a different frequency, we have to combine a photon at our gate field with a photon at our input field, like so. And destroying those, we can generate a signal field. Now, because we've gotten rid of all of our signal field, this process will reverse and go the other direction. So that in effect, we actually just have an exchange between the signal in and the signal out. And we can treat the gate as effectively undepleted, just a classical field with some energy. All right. Now, say that I want to perform this summer difference frequency process, and I just throw my light into a nonlinear material that has a high-2 nonlinearity. I mix my gate field here with some input field, and then what I find is the process is actually really efficient. So I get these conversion and back conversion cycles that are really far from full efficiency. And the reason for that is wave-vector mismatch. So what this says is that as my fields propagate, I'm going to generate some of the signal that I have. Then there's going to be a phase slip between that signal and the newly generated signal as I propagate. This is going to cause a sort of interference to where I get these conversion back conversion cycles between my different fields. So there's a process that we use called quasi-phase matching, in which we invert the sign of our chi2 nonlinear material so that we can mitigate this phase shift. So every time my field is going to back convert, I flip the sign of the interaction and it starts converting again. It begins to back convert, I flip the sign of the conversion and it starts converting again. This process was first proposed way back in the 1960s, but then was demonstrated by Marty Bayer and back Rowe in lithium niobate bars. All right, so that's pretty much the nonlinear optics. What we're going to do now is kind of build up these programmable ultrafast nanophotonics, and then I'll describe how those nonlinear optics can lead to creating an ultrafast gate. So there's a whole lot of different nonlinear materials that we can choose to have this quadratic electric susceptibility. But there's certain constraints that we want to impose to pick a good one for making this. So if you look at this list here, there's only a handful of these that can actually either be quasi-phase matched or at the same time have low price. So it's imperative that we have these two features in order to have efficient nonlinear interactions that aren't lossy. And if we look over here at the effective nonlinearity of these interactions, we can see that the MgOLN, which is our lithium niobate, is one of the most nonlinear materials that we can do chi2 interactions in. Whereas the silicon and silicon nitride E-fish are way down here, where we can't actually get efficient nonlinear interactions. Okay. So a lot of the development of lithium niobate thin films has happened here at Stanford. A large part of it has been done by Spatiani's group. And they've not only been improving the fabrication of these devices, but also demonstrating all sorts of nonlinear devices. Here's only a small sampling of some of the work that they've done. For instance, they've greatly enhanced the hue of resonators in order to boost the efficiency of these nonlinear processes. They've created spectroscopy sources that can be tuned over an octave of bandwidth from 1.5 to 3.5 microns. And they've also employed electro-optic modulators within these OPO cavities in order to create ideal spectral shapes for broadband frequency. Now, if we really want to make these nonlinear processes efficient, what we want to do is we want to take our laser fields and we want to compress them down in time. So if we take all of our photons and we push them into one moment in time, get these extremely intense laser fields. And since my mixing process is nonlinear with the intensity of my laser field, that's going to boost the nonlinear mixing. So one thing that we have to do, which is really actually a huge advantage working in films, is that we can engineer the dispersion of these devices by controlling the geometric parameters of our waveguides. So by changing the top width, the film thickness, and the edge depth of our devices, we can change how much of the electric field overlaps with our nonlinear thin film device and the substrates that surround it. This allows us to control both the group velocity mismatch, which is how fast my pulses separate from each other in time, as well as the group velocity dispersion, which is how fast each pulse itself stretches out in time. So by making both of these zero, we can basically make these pulses propagate forever, staying overlapped in time, not stretching out. And what that has allowed us to do is increase the bandwidth of a lot of these nonlinear processes by about an order of magnitude over the other conventional waveguide devices that we had, maybe 5 years ago. And this is also because of the extremely tight confinement. You can see these waveguides are usually on the order of a micron. We can get these extremely high field intensities with very low pulse energies. And so with only 50 femtojoules, we can do extremely efficient second harmonic generation. All right. And a lot of this work has been pioneered by Mark Jankowski, and there's many other works, of course, that have come from him and out of the Bayer lab on these ultrafast nonlinear optics. All right. So all of these sort of advances have gotten people anticipating nanophotonic circuits, where we can, do computations or build new computing architectures. For instance, in this work, these authors are imagining an optical DRAM where we have a cavity where we can store a pulse. We can top it up using optical parametric amplification. And the idea is we want to gate it out using some different frequency generation. I'll talk a little bit more about how gate works, because this will be the kind of the point of the rest of this talk. But what they've shown here is that you can do things like solve the Boolean satisfiability problem using these sort of all-optical frameworks. In addition, people are also matching different frameworks for coherent Ising machines. That's a device that was demonstrated over in Stoker about a decade ago. And what that does is it can allow us to build a computing framework that can solve all sorts of optimization problems much, much faster than a conventional classical computer. So these smart guys right here have imagined different ways of building this coherent Ising machine, employing some nanophotonics. And the idea here is that if we combine squeezing and one of these sum or difference frequency generation processes, we can employ an all-optical multiply and accumulate, which can do a lot of the sort of feedback that we need in these coherent Ising machine systems, but all optically. So to make these things work, we need to be able to build ultrafast optical switches based on these nonlinear processes. So the first stab at this was by the Morani group over at Caltech. He was one of the original people who worked on the coherent Ising machine. And the idea here is that we're going to use second harmonic generation to switch pulses between waveguides. Now, if my pulse is really weak, it's going to propagate along, and I'm not going to be able to convert it to the second harmonic because of the low intensity. And then what that's going to do is basically lead it to go past this directional coupler in one direction and avoid coupling it the other. However, if basically it's going to end up coupling over to this waveguide and going out here. However, if I have a really strong input, I'm going to efficiently convert this to a second harmonic at a different frequency. It can then bypass this directional coupler, and at that point back converts to the original pulse. All right. And what they showed is that this device operates, this is basically the fastest switch that we've built. It operates on a 100 femtosecond time scale with only 100 femtojoules of energy. So it's extremely energy efficient and extremely fast, which is why we want to go this route of all optical. Now, one of the challenges with this is the switching in this device depends on the actual state of the bus. If I have some quantum state that I want to switch between buses or something while we're switching it, I can't rely on the state itself to switch. I need some external controllables. And so most of the rest of this talk is going to be talking about the process that we use to design these ultra-fast optical switches for doing this stuff. So One of the challenges here, or some of the challenges, are that we need to choose the wavelengths so that we can have strong nonlinear interactions. As we push towards the band gap of Tiflin and work in the visible, we can have stronger nonlinear interactions. But it gets a lot harder to do this dispersion engineering that we need to do for ultrafast nanophotonics. And what that does is it can largely limit the bandwidth of the operation. And so we can't have these 100 femtosecond switches. It's going to be on the scale of picosecond or more, time scales that conventional electronics. We also want to be able to preserve the spectral amplitude and phase information over octave spanning bandwidths, which correspond to the sort of time scales that we're working at. So we want to be able to fully efficiently transfer both the amplitude and phase of whatever input light we have between buses or waveguides or whatever we're switching to. All right. Another problem is that these nonlinear frequency conversion processes, so even the second harmonic process, when you work with pulses, it actually is a convolution of the spectra. And so what that can do is it nonlinearly distort your input light. So we need something that can, linearly transfer these things instead of nonlinearly. All right, and then the other thing is that these distortions can lead to asynchronous conversion cycles across the envelopes of my fields. And I'll talk about this later, but that eventually will lead to a supercontinuum generation, which is not good if you want to preserve any information for your pulses. So let me talk about the method that we're going to use to basically solve all of these problems. So the device we have here is effectively one of these optical DRAMs. So I have a cavity right here, and this red pulse is my signal. It's being amplified by this green pulse, which is basically topping it off. And what we want to do is we want to get this pulse out of the cavity so that we can use it for computation or, as a quantum resource or whatever it is we're going to do with this light. So the way that we do that is we come in with this gate pulse and we flip the frequency of the signal pulse so that it can bypass this directional coupler. We've designed the directional couplers effectively to be dichroic, so the red pulses will stay inside of the cavity. When I flip the frequency to be the blue pulse, it can now exit the cavity. All right. Now, this process employs what we call adiabatic frequency conversion or adiabatic sum frequency conversion. That's a process that has been studied both by the Thayer group and many others. It's been studied in the case of adiabatic OPA, where you have amplifiers that employ a swept or chirped grading period, or quasi-phase matching is swept in order to phase match a lot of wavelengths. And that can dramatically increase the bandwidth. In the case of adiabatic sum and difference frequency generation, it not only increases the bandwidth, but in a sense it linearizes the dominant process, which I'll talk about. All right. So some advantages of this is that we can increase the bandwidth so far that it effectively can fill the entire transparency region of our nonlinear material, so we can get massive amounts of bandwidth and operate on extremely fast timescales. I'll talk about how it can allow us to engineer the dispersion of our pulses through the quasi-phase matching design, which sort of alleviates some of the pressure and the challenge of dispersion engineering in visible. The linearized conversion will preserve our amplitude and phase of our pulses so that we don't distort things. The conversion is unidirectional, so I don't have to worry about basically designing my device so that it cuts off exactly when I'm converted, so I avoid back conversion. These devices I'll talk about are also quite robust to fabrication errors because any sort of perturbations are still going to get converted. All right. So basically the end result of this is that we're going to be able to take 40 femtosecond pulses that are anywhere from 1 photon to maybe 100 femtojoules. And we're going to be able to convert those with full efficiency, or we can effectively tune the efficiency by tuning the power of our gate pulses. So effectively what this thing is going to act like is a beam splitter. All right. So to start off, let's go a little bit more in detail about some frequency generation in the context of ultrafast pulses. So if I have CW light, so just a continuous wave laser, I have some gate pulse that I'm using to drive this process. I have an input frequency and I want to convert that to an output frequency. If I mix with this narrowband gate, I have this one-to-one frequency correspondence between my input frequency and my output frequency. And each of the different frequencies are just going to be shifted. So this is just a linear shift in the frequency from the input to the output. And the idea is I want to be able to shift the entire bandwidth of my pulse from one center frequency to another center frequency without perturbing the envelope or the phase or any of that kind of stuff. Now, one of the challenges, though, is that quasi-phase matching, this way that we get these processes to be efficient, it only can perfectly phase match one process. So what happens is I get efficient conversion for this center wavelength, but if I look at the other wavelengths of my pulse, they're going to be extremely inefficient. And a lot of the people here, you probably are recognizing that this looks exactly like Rabi oscillations. And in fact, you can use a lot of the same intuition here. These systems are SQ symmetric. It's a two-level system. And so effectively, I just have a two-level system between the input frequency and output frequency and oscillations between those. And what you're seeing here is that as I change the detuning, I reduce the amplitude and increase the frequency of the detuned Rabi oscillation. Okay. So the other thing is that if I want to have high conversion efficiency in one of these quasi-phase match devices, I need to cut my crystal right here. And what I'm going to see is that I actually have a relatively narrow bandwidth to compare to if I had a shorter crystal that I cut right here. I could have a broader bandwidth, but with less efficiency. And this is effectively what we call the bandwidth efficiency curve. So now actually, borrowing from a lot of work that has been done in quantum systems and NMR and all that kind of stuff, we're going to use the adiabatic frequency conversion to make this more robust and to broaden the bandwidth of our nonlinear process. So you can imagine like in a two-level electron system where I have spin up and spin down. Normally I use microwaves to get that to oscillate between spin up and spin down. But if I trip those microwaves, I can basically make the spin do this little spiral from spin down to spin up. And that's a really robust way to prepare quantum states. In the same thing, or in the same kind of vein, we're doing a sweep of the quasi-phase matching period. And that's going to lead to a really robust transfer of energy from the input gate. All right. So if I take a slice of the way this looks, is my light propagates along and then is suddenly very rapidly converted from zero efficiency to full efficiency. This process is known as rapid adiabatic passage. To get high efficiency, I need to make sure the intensity of my gate pulse exceeds the sweep rate. So if I sweep faster, I need to increase the intensity of my pulse. And if I look how this looks at all my mixed frequencies, I can see that each wavelength of my light is getting fully converted, but at different positions within the device. One of the reasons that this is robust is that if there's some fabrication error and the quasi-phase matching period is off or the dispersion is a little bit different, all that does is it shifts around the position that these convert, but it doesn't prevent them from converting. So one of the first people to show that this process obeys the Landau-Zener theory of rapid adiabatic passage was my former PI, Jeff Moses. And what he showed is that as you turn up the pump intensity or the gate intensity of this process, you will saturate it, reaching full efficiency. Effectively, there's a threshold beyond which you can saturate it at 100% level. This is great because if you have any sort of intensity fluctuations and you're operating beyond this point, it's not going to change how much conversion efficiency you have. Whereas in normal nonlinear wave mixing, it can amplify a lot of the fluctuations or non-idealities in your system. because of basically the nonlinear dependence on the intensity. Yeah, good.
Does the phase of the pulse get correlated with the intensity beyond that point?
No, so there's effectively linear transfer of the phase. And so, well, okay, technically, if you drive it extremely hard, you can have some sort of cascading effects that will lead to a nonlinear phase shifts. But you basically operate it, right around the switch. So effectively what this has done for us is it gets rid of the bandwidth efficiency trade-off and exchanges it with a power device length trade-off. About 7 or so years ago, there was an experiment demonstrating that you could use this to generate extremely broadband infrared pulses. So Peter Krogan et al. Generated some octospanning mid-IR pulses and was able to compress those all the way down to 10 femtoseconds. He also showed the linear transfer of amplitude and phase of these devices by pulse shaping in the near infrared before the conversion device. He created a pulse pair and showed that property held when it was converted into the mid-infrared. This is extremely convenient for ultrafast science because there's a lot of technology that's been developed around the near infrared that doesn't exist in the mid-infrared. So this allows us to use all of the abundant technology to shape our near infrared pulses, and then you can transfer that stuff to the mid-infrared where you can't do these sorts of manipulations. Now, one of the problems that they found with this experiment was that the ADM devices were actually they seem to be totally distorting the dispersion of the device to where they had to apply really complicated functions in their pulse shaper to mitigate the dispersion. And this actually was studied quite a while ago, back in 2005 in Marty Bayer's group. It turns out that the dispersion imparted to your pulses depends on the specific design of the pulse. In fact, Charbonneau-Lefort proposed a scheme where in an adiabatic OPA, you could completely cancel out the material dispersion of a tandem device to where you could build an amplifier that doesn't have any material dispersion. And on top of that, was also able to use this for shaping the gain. All right. So we're going to adapt this idea to the adiabatic sub-frequency devices we have. So the idea, basically, the way that this works is that because the conversion in my device is nearly instantaneous, I can treat the total group delay of each wavelength as being a sum of the group delay of the input field plus the sum of the group delay of the output field after the conversion position. All right. So then what that means is that we can have a very simple equation that describes the effective dispersion that's imparted by our device. But not only that, we can design the device to impart a particular dispersion. So by solving this equation for the conversion position, we find that if we engineer our conversion positions for a specific group delay, we can get whatever output dispersion we want. Okay. And then effectively we can see how this converts into, or we use basically our phase mismatch as a map for which frequencies should occur where, and that gets us our full instructions. A little bit different. Okay, so what this allowed us to do back in Jeff Moses's group is take a device which, if you sort of naively designed it with a chirp grading period, would chirp your pulse out to 5 picoseconds. But we designed it so that it would take a 10 femtosecond input and produce a 10 femtosecond input or output, sorry. So instead of stretching that 10 femtosecond pulse to 5 picoseconds, it effectively applies no dispersion to it. Okay. And the way you can kind of think about how the device works in the time domain is that the first period or the first section of the device before the conversion is effectively a pulse stretcher. So we're stretching our pulse out until it gets to conversion position. We then convert it from the input frequency to the output frequency. And the last part of the device compresses it back down. So this is how we get a 10 femtosecond pulse in the near infrared to a 10 femtosecond pulse. And we experimentally demonstrated this, showing a 11.1 femtosecond near infrared pulse can transfer over to a 11.6 femtosecond mid infrared pulse with an octave of bandwidth. So, all right. So the last thing about designing one of these adiabatic devices, we're kind of putting all the pieces together here, is that we need to choose a dispersion engineered profile. So if we don't do anything, we just send our pulses into some lithium niobate waveguide that we not paid any attention to the parameters of. What we're going to find is that we have group velocity dispersion, which is stretching the pulses out. And we're also going to have group velocity mismatch, which is causing these two pulses to separate. If my pulses stretch out, that lowers the intensity, lowers the strength of the interaction. If my pulses separate, they can no longer mix with each other because they're not overlapping time. So what we can do is we can tailor the film thickness, the crop width, and the edge depth of our device to give us a particular dispersion profile. In this case, we've effectively canceled out the group velocity dispersion and group velocity mismatch between the input and gate, so they will travel together. But we've left the dispersion of the output to be an extremely large value. And this is what I was saying at the beginning, is that for visible pulses, it's really hard to get the dispersion engineering to work. Or at the very least, we can get the dispersion engineering between two pulses, but it's hard to get that third one to work out. In addition, it's a lot more sensitive to the fabrication of the device. So what we're going to do instead is we're going to use the technique I just talked about, which is using the quasi-phase matching grading in order to engineer the dispersion of the device. Okay, and the very last thing is some work shown by Chris Phillips, which is anytime we're coupling into modes, we want to apodize our device so that we can really smoothly couple into the eigenmodes of the system. And that's about all I have to say about that. Okay, so here's the experiment here. We have a 40 femtosecond, 100 femtojoule telecom pulse. We want to mix that with a 1 micron, 100 femtosecond gate pulse, which we're going to vary the energy of. And we have two options for designing the quasi-phase matching structure that's going to convert these pulses. So either I can go for no dispersion on my pulse at all, meaning that it's going to get stretched through the device, which is this blue curve. But what this shaded region is telling me is that where the conversion is happening is in this very high slope area of the quasi-phase matching device. If instead I accept some dispersion on my pulse, so it stretches out in time to say 250 femtoseconds by applying this 600 or 6,000 femtosecond squared of anomalous dispersion, then I can greatly extend the conversion region of the device and slow down the chirp rate. And by Landau's Zener theory, that's going to reduce the pump intensity I need to get to a certain efficiency of my device. All right. So what I see now, if I put some light in this device, I'm going to send in some pulse that has a spectrum that looks like this around the telecom. You can see that each wavelength is getting converted at a different position to generate my output wavelengths in the visible. And in the time domain, you can see that my pulse is propagating along. I've engineered it so that it doesn't stretch out and it doesn't walk off from the gate pulse, so it just stays like this. And it generates my signal pulse, which I haven't used geometric dispersion engineering, but I've used quasi-phase mapping dispersion engineering to get a particular temporal profile of the output. All right. So this then is how I'm able to do what I showed you at the very beginning, which is take a 40 femtosecond 1 to 100 femtojoule pulse, combine that with my gating pulse to create an output that has some easy to remove dispersion so that I can get it back down to 40 femtoseconds. We also talked about how the number of photons are preserved between the input and output. So every input photon that's converted becomes an output photon with a linear transfer of amplitude and phase from the input to the output. And I can control the conversion efficiency, or basically how much of the pulse is switched either between buses or in and out of cavities by controlling the energy of my gate pulse here. So effectively creating a all-optical pumped beam splitter to split between cavities. So let's go ahead and talk about just a couple of the challenges of scaling this stuff to Few-Photon, and then maybe some of the ideas that have come about for making this. All right. So here's a recent experiment that we did over in the Bay Lab. What we have is a thin film lithium niobate device on sapphire. We have a 2-micron pulse, it's about 40 femtoseconds in pulse duration. And we're sending that into the waveguide. And we want to perform second generation or second harmonic generation on this pulse. So right here is my pulse at 2 microns, and I want to generate a pulse at 1 microns. And I see that I'm actually getting all these other wavelengths in my device. And not only that, but the bandwidth of all these wavelengths is broadening until they start to interfere with each other. So what's happening here on the large scale is that when I perform nonlinear processes, it's not just the one process that I want to happen. It's all of the processes happening at once to varying efficiencies depending on their phase mismatch. So in this, I'm generating the first and second harmonic, but then my first and second harmonic fields combine to create the third harmonic. For the fourth harmonic, I can either do second harmonic of the second harmonic, or I can combine the first and third harmonics to create a fourth harmonic, and so on to the fifth, and maybe even the sixth harmonic out here, the transmission edge of the device. In addition to that, in addition to the harmonic generation, the bonding mechanism is a little bit more subtle, but this is a work led by Mark Jankowski to study why this happens. And the reason is that if I have a broad bandwidth that I'm putting into a nonlinear device, the temporal profile of that is going to convert to different positions depending on its intensity. So what happens is my temporal profile effectively gets modulated. And what those modulations do is they actually are creating new frequencies. And so that's the broadening mechanism for this process, where you can see over here in comparison to experiment versus this model. So as this propagates along, you can see the modulations, and that leads to the broadening of both of these spectra to create this supercontinuum, which is really pretty to look at. But if you're trying to use this process to modify or manipulate, say, like a quantum state, what this means is that you're just going to completely decohere the thing, and you're going to couple to all of these higher order modes, and everything is just going to be a total multi-moded mess, and the device isn't going to do what you wanted it to do. So one of the proposed solution to fight the multi-modedness of these pulses at a time is actually this idea of a temporal frap. So if you think about a waveguide is effectively a 2D finite well. And as you squeeze that well tighter and tighter, constricting the boundary conditions, the eigenlevels will separate out. And that makes it easier to couple into just one mode of the device. And so single-moded waveguides are just a really tiny core with a cladding. You have an index contrast, which creates your finite well, and that allows us to couple into a single. So what we need to do here, what they propose in this work, is to create a waveguide in time. So the idea is that we can use cross-space modulation, which is a high-free nonlinear. And what that does is it modulates the index of refraction of that a pulse experiences depending on the intensity of the pulse. So what that means is that under this pulse, I actually get an index of contrast that is moving along my waveguide. So what that does is it separates out the eigenlevels of my temporal modes of the pulses that I actually want to mix together, and effectively creates a single mode waveguide in time that moves along with the process that I care. All right. And what they found is that this also can help us greatly increase the nonlinearity of these interactions. They're predicting that they can get a greater than 1 nonlinear coupling to loss rate, which is necessary for doing any sort of extreme nonlinear optics with quantum states. And so here's the results they find here, which is orders of magnitude beyond what has been shown so far. So we're highly motivated to pursue this sort of device.
Is that experimental or theoretical?
This so far is theoretical. Yeah. There's a lot of challenges of experimental. All right, so that effectively brings me to the end of the talk here. So what I've told you about so far is a bunch of different nonlinear optics, in particular adiabatic sum generation, which allows us to create these really robust switches that we can gate asynchronously with pulses in and out of cavities between buses. They lead to a linear transfer in the amplitude and phase of my pulses between different frequencies, and they also operate on ultrafast time scales, like sub 100 meters. I showed you our designs, which should be able to convert 40 femtosecond pulses in the telegon to be visible. And to get to shorter pulse durations, we basically either need to make the devices longer or just go to higher quantum intensity. So it's a sort of design trade-off and not a physical limitation. So what this does is it paves the way to fully programmable all-optical computers with octave spanning bandwidths, and to mitigate some of the realities of these processes, we can potentially use temporal graphs. All right, and finally, I just want to thank these guys for their constant help and guidance, Mark Chukowski, Edwin, and Tim, as well as Tadeo and Marty Wolf. All right, thank you. Any questions?
There's none.
I was just wondering, you showed like the very steep conversion efficiency as function of length.
Oh yeah.
But does that mean that you're actually kind of not using quasi-phase matching, but that it's like only very short period in which you have conversion and then it stops?
Yeah, it's a really good question. So effectively, I have this quasi-phase matching period. Normally, I would design it so that the phase match is 0 across the entire device. But what I've done here is I've designed it so that the phase mismatch is close to negative infinity at the beginning. It goes through 0 at some point within the device, and then it goes off to positive. And so what this allows me to do is have this rapid adiabatic process right here, where I rapidly convert from the input to the output. And then most of the rest of this device is just suppressing the ripples. So it's trying to couple out of the, I basically have 2 coupled eigenstates. I need to start out here, slowly go through the coupling region, and then over to the other side.
Henry mentioned.
Sorry if this was explained, but how was this waveguide and time supposed to be incorporated into the earlier part? Is it supposed to be part of the gate?
Yeah. So it's depending on sort of what sort of feature show up in the gates, you could implement it there, but really it's going to be useful for the it's going to be useful for this portion.
Okay.
So I'm going to have some OPO that's being pumped by this guy right here, and this is going to be driving all sorts of sort of temporal dynamics. And the original vision of this was to mitigate the higher mode temporal dynamics there.
Okay.
So going back to that slide that you just showed, yeah, so you made a comment that you could store quantum information in that ring. And I guess my understanding of the OPO is that you're using that to continuously refresh the pulse. So if that's the case, you really can't use it for as a quantum.
Yeah. So as a DRAM, it's not necessarily going to be storing quantum information. You're going to potentially be working with like really low energy, classical pulses with that. For the quantum side of things, it's more going to be used as a quantum resource, where you can run this thing below threshold, get some sort of quantum state in the device. And then instead of relying on, say, like a 10% coupler, which has all sorts of, things that distort the quantum state, so that what you're getting at is not exactly what you have in the cavity. You can instead, flip the switch so that you do get all of the, quantumness in the cavity out. Yeah.
Another question.
Yeah.
Okay, so my second question relates to this question of getting down to single photon nonlinear.
Yeah.
So I guess there are material questions, but there's sort of to me, a more fundamental question, which is, what should I think of as the cooperativity limit for the performance of this conversion process?
What do you mean by cooperativity?
So there's some, in cavity QED.
Yeah.
What we do is we compare like the unitarity limited cross section for the collision between photons or whatever to the size of the waveguide. And then if there's dispersion engineering, such that things effectively go back and forth past each other, meaning a cavity or an engineered waveguide, you multiply by the number of passes. And that's sort of the best you could possibly hope to do.
Yeah.
So I guess maybe the question is, what is the best you could possibly hope to get? If material things weren't getting.
I mean, if we, I guess there's a lot of different things you can kind of imagine. I don't think that lithium niobate is probably going to be the one that actually produces some, useful quantum device, but it's a good platform for studying these effects so that when, some like heterostructure or something comes around with engineered asymmetric quantum wells to get really large I2 values, maybe you can use that to have really strong nonlinear interactions while using all these different effects to mitigate the problems that we're experimenting with studying. But these are kind of realistic estimates where you're just starting to get to, Judith over half of 1, which is where you can actually use this for useful new, quantum processing or state generation. And really, we probably need to be like a couple orders to like a scientifically useful device. Yeah.
Any other questions? All right, well, thank you.
Thank you. Oh, really? Yeah.